Okay, I think we can start now. If anybody joins later, then they will join. And thank you everyone for coming to this seminar talk. And it is my great pleasure to introduce Son Raymond. He's a researcher at Bordeaux University in France, and he will talk about today the solar system giant planet instability, dynamical trigger, and implication for Planet 9. And before we begin, you can ask questions after the talk. And if you would like, you can write the questions in the chat during the talk, and they will be then answered after the talk. So without further ado, you can start, Son.
Okay, thanks. Thanks. It's a pleasure to be here. So it's nice to be here. So I'll talk today a little bit about the giant planet dynamical instability in the solar system and different aspects of that. And so we'll start you off with a little GIF I made for the there's not enough cartoons of the instability. It's a pretty fundamental thing in the solar system, and we don't have enough cartoons of it. So here's another one for you. So before I get started, kind of the main collaborators on what I'm going to talk about are listed below, especially Nate Cabe and Andre Isidoro, as well as these other people. So, oops, here we go. So here's an outline of kind of what I'll talk about. First, I'll talk about kind of the dynamics of dynamical instability and what dynamical instability really means. Then talk about the solar system's dynamical instabilities, and then kind of we'll look out at some new stuff related to Planet Nine and planets on very wide orbits, similar to what Planet Nine is proposed to be on. So I'm not going to talk about the formation part. So I included this one slide about planet formation. And in this talk, I'm not going to talk about it at all. So it's nice. I spend forever talking about all these different steps of planet formation, and I know some of them super well. But we're going to skip along that this time. All right. So we're going to start kind of the starting point that what I'll talk about will be basically pretty much fully formed planets. I'll talk a little bit about planet migration, which happens, when a planet gets big enough that it's very massive, say at least, in this case, it'll be at least like ice giant mass, while the gas is still in the disk, and so the gas can cause it to migrate. But most of what I'll talk about will be after the gas is gone with pretty much fully formed planets. So to get started, we'll talk about dynamical instability. Technically, a dynamical instability is really just when the orbits of two objects or two planets cross, right? And so, all right, that's the instability. And so what happens, right? We like to think of instability as leading to something disastrous, and it does. So what kind of disasters are we talking about? Well, it can either typically be gravitational scattering, right? And so in this cartoon version, scattering would be that one planet was ejected and then another planet survives on a very eccentric orbit. Or the other outcome is it can be collisions, right? So sometimes the two planets end up in the same place at the same time and they bash together. So first question is, why do these things happen? What dominates scattering versus accretion? And so to illustrate that, let's start with a simple cartoon of you got Jupiter orbiting a star or the sun and a little asteroid. And the question is, what does it take for Jupiter or this planet, whatever this planet is, to be able to eject this asteroid? And it's pretty simple to figure that out, right? What it needs is to give a gravitational kick to this small body so that it changes its speed enough to go away and never come back, right? So to go away and never come back means that that object needs to reach the escape speed from the star. And the magnitude of the kick that the planet can give is actually the escape speed from the planet's surface. That's the biggest change in velocity that a planet can give to something, at least in one encounter. And so those two are the key quantities, basically the escape speed from the planet's surface and the escape speed from the star at that distance. And the ratio of those is basically called the Safronov number. I'll talk about it in a sec. But this is kind of just to summarize what I said. To eject something, the escape speed from the planet needs to be bigger than the escape speed from the system at that planet's orbit. And so that leads to this thing called the Safronov number, which is just the ratio of these quantities, the ratio of the escape speed from the planet to the escape speed from the star. And you can put numbers on it like that. So for Jupiter at 5 AU, you can see this value of this number is about 10, right? In terms of the square of the escape speeds. And in simple terms, when this number is big, right, that means the escape speed from the planet's surface is bigger than the escape speed from the star, so scattering dominates. It's more likely to eject things rather than have them collide with you. Even though collisions can happen sometimes, but scattering dominates. And when the Safronov number is low, which is the case for kind of lower mass or closer in planets, then collisions are dominant. And so in kind of parameter space of mass versus orbital separation, what this plot shows is kind of where ejection or accretion dominates. And so, I drew the Safronov number of one curves for two different planet densities. So, there's a little bit of wiggle room. But you can see, to the left for small planets close to the stars, accretion dominates. For gas giants further out, ejection dominates. And this is where the planets in the solar system are located, right? So you can see among the terrestrial planets, everything bashes into each other. Among the giant planets, things eject each other or scatter. And you can also imagine, right, if Earth was moved out to 100 AU, all of a sudden it would be ejecting things. And if Jupiter was moved in to become a hot Jupiter, all of a sudden it would be crashing into things, right? So it's a combination of both the planet's characteristics, and where it is in the system. And of course, we think that planet-planet scattering is a key force in shaping exoplanet systems. Here's an awesome animation by Eric Ford showing dynamical instability where the two outer planets in the system, their orbits have been perturbing each other. Now their orbits are just about to cross. They have this series of close encounters here. And in the end, the velocity that was given to one of the planets, is more than the escape speed. It's ejected, and the survivor has this eccentric, stretched out orbit. And I like to say that the kind of the stretched out orbits of giant exoplanets are kind of like scars from their violent pasts. And this is the violent past, right? This dynamical instability, the scattering event. And so if you look at the population of giant exoplanets, they have a humongous range in orbital eccentricity. And so you can see where our Jupiter is. Our Jupiter is nice and, nearly circular. It has an eccentricity of about 5%, but the median for giant exoplanets is about 25%, and it goes up to basically one. All right, the highest eccentricity that's well characterized, I think it's like 0.97, something like that. It's super high, right? And we think that this is really caused by scattering. So a cool thing about this that I think is really kind of elegant in some sense is that current thinking about how planetary systems are shaped really comes down to the dynamical instability. And there's two different regimes. So this cartoon just kind of shows a simple illustration of the story of how we think planets are forming, right? These cores grow past the snow line, they're bigger, form gas giants. They tend to migrate, probably end up in chains of orbital resonances while the gas is still there. The gas goes away, they go unstable, and we get the giant exoplanets like we see, right? The kind of story I've just told you. What's interesting and is that this Safronov number plays a key role and shows that this evolution of giant planets is probably pretty much exactly the same for super Earths. And so for super Earths, the current model that we have is called breaking the chains, which basically proposes that there's an early phase of the growth of cores of much smaller, embryos, sometimes rocky, sometimes with some ice. They migrate to the inner edge of the disk. They end up in long chains of orbital resonances. And then the gas goes away. They have a big dynamical instability. But instead of ejecting each other, these planets can't eject each other. They crash into each other because they have low Safronov numbers. And so then we end up with, super Earths like we see today. And this model, the breaking the chains model, can explain the properties of super Earths super well. And I just think it's really kind of cool that the same evolution of, probably a phase of migration to get planets close to each other, gas disk goes away, dynamical instability leading to either collisions or scattering can explain, you know, all these populations of planets. It's pretty cool. So, uh, like I said, I already said these words, so we can skip this stuff. So there is a kind of philosophical question. Why do you think a planetary system would go unstable in the first place? And so you can imagine, you know, in some sense, I think this is the wrong question because, you know, to get a planetary system to form in the first place, it has to go through it has to grow. Planets have to grow bigger. And the growth process is essentially a series of dynamical instabilities. And so for a certain point of view, right, if you had a bunch of dust grains orbiting the star, they can only grow when their orbits cross, so they can collide and get bigger, right? And so in some sense, there's these dynamical instabilities constantly throughout the planetary growth phase. And the question is really like, how does the system know when to stop being unstable? And it's a tricky, right? It's a sort of philosophical question, but you can address it in some mathematical terms. You could say, when the time scales for orbits to cross exceed the lifetime of a system, maybe then it knows to stop going unstable, and so on. Anyway, there's different ways to address it, but I think it's an interesting philosophical point to realize that dynamical instability is not some rare, weird thing. It's the norm, and stopping it is the weird thing in some sense. And of course, there are some systems out there that do seem to be remarkably stable, right? And it's hard to tell which systems are stable and which ones are not because we only see snapshots in time. But there are some systems, like the TRAPPIST-1 system, that seem to be trapped in these resonant chains, these long chains of resonances between planets in a given system that we think are basically signposts that these systems have stayed stable at least since their formation, right? Since the gas disk that created the resonant chain by migration went away. And so it's interesting, right? There are some counterexamples where the system, obviously there were some instabilities to form the planets, but then the system stayed stable for a long time. All right, now let me transition and talk about the solar system's dynamical instabilities. And I'm saying that in the plural sense because there's kind of two key ones I want to talk about. So the first one's the accretion of the ice giants, and then the second one is the one that we more commonly call the dynamical instability, right? So the accretion of the ice giants, this we think happened, kind of a key phase happened late, shortly before the gas disk dissipated. So I said I wasn't going to talk about formation at all, and I guess I was slightly lying because we're talking a little bit about it here. But in any case, here's kind of like the last couple million years of the lifetime of the gas disk around the sun. So we think Jupiter and Saturn were already formed, and the ice giants were, kind of their cores were already grown, but they weren't ice giants yet. And so here's a simulation showing that. There's a gas disk here. Jupiter and Saturn are fully formed. And then there's this population of something like 10, 3, 4, 5-ish Earth mass cores. They're icy cores, the progenitors of the ice giants out past Saturn. And so these things are subject to forces from the gas in the disk, and so they migrate. And so what happens is basically the ice giant cores migrate towards the gas giants. The gas giants act as a barrier because they've carved a gap in the disk. And it's basically smashing a bunch of things into a wall. They don't all get squished into one planet, but you'll see what happens. So here's kind of the evolution of a simulation. So these things migrate inward, they get blocked by Saturn. Sometimes you'll see one of them get thrown up in eccentricity. That means it's got too close, it got scattered by Saturn or Jupiter, and it's getting ejected. But the ones that survive bash into each other and they end up, you don't end up with 20 planets left, you don't end up with one planet left. In successful cases anyway, that look like the solar system like this one, you end up with three, which are three ice giants, each, about 15 Earth masses like the real ones. And they tend to survive in the end, always in resonance, just because migration squishes things together, and the stable place to be when migration happens is in resonance. And this kind of simulation does a really nice job of matching the ice giants. It matches their masses well, and there's a couple other key factors, right? And so here's what the end of the simulation looks like at Jupiter, Saturn, and three ice giants, one of which will go away later, like we'll talk about. And the cool thing is that you need this phase of collisions to explain things like the obliquities of the ice giants, right? So we think there really had to be a phase of big collisions among these objects rather than, ice giants just being formed, solely by something like pebble accretion because their obliquities are so high. And a key kind of byproduct of this that'll come back later is that during this process, about half of the total mass in those cores was ejected, right? And it's typically, in terms of number, it's like, five, something like that. And a total in mass, it's, maybe 30, 40-ish Earth masses ejected. And that's what you need. You need that as kind of a byproduct to explain what we have. So now let's move on to kind of the main dynamical instability, sometimes called the Nice model because it was originally developed by researchers in Nice in France. And here's kind of a simple cartoon of what it looks like. So the initial conditions here basically come straight out of that animation I just showed you. There's Jupiter, Saturn, and three ice giants. And then there's an exterior ring of planetesimals. And these are basically comet-like planetesimals, kind of the primordial Kuiper belt that we think had to be there to explain what we see today, yeah, for both dynamical and reasons, and also to match the actual Kuiper belt objects that we see today. And so the assumption here is like that the ice giants formed as we saw before, but they don't stay that way because we don't have a third ice giant in the solar system today. So the what the animation this looks like is basically there's some kind of phase where instability is setting in. Boom, the instability here was very rapid. You saw one ice giant being ejected, and all of a sudden that nice green ring has disappeared. It's being scattered everywhere. That outer disk, that outer primordial Kuiper belt gets completely removed. It gets almost entirely ejected. Some ends up in the Oort cloud. The rest of it's gone pretty much. And the planets at the end are basically on their present day orbits. And the byproduct here is that one or maybe even two extra ice giants were ejected in the process. And that'll come back later. And why do we think this instability actually happened, right? This seems kind of like a weird story to tell about our solar system. And there are good reasons. And so what are the reasons? So the key reasons is that number one, uh, the instability can match the giant planet's orbits. It's the only model that I'm aware of that can do this. And it can really do a good job of getting the planets in the right place, starting from conditions that make sense in terms of how the planets formed within a gas disk. Can explain other small body populations, especially like the inclination distribution of Jupiter's Trojan asteroids, which are hard to explain otherwise. Can explain the capture of the irregular satellites of the giant planets, and things like the orbital structure of the Kuiper belt. Right? There's a lot of little details. Each of these points has a zillion little details that you're free to ask me about later. But the kind of the big picture is that the dynamical instability model is the only one out there that can explain all these different features of the solar system at once. And it's not perfect, and it's always being tweaked a little bit to try to do things a little better. But the concept of a dynamical instability that ejected an early, a third ice giant, spread out the planet's orbits, really makes a lot of sense. It seems to match a lot of things. Now, when did it happen? Right? And so this is a big question that has sort of changed over the past decade or so. And it comes down to analysis of the bombardment history of the moon. So here's a picture of the moon. And what you see there, those numbers in pink are Apollo landing sites, where the Apollo missions took samples from the moon and brought them back. And the blue ones are the Soviet Luna missions that also grabbed rocks from the moon and brought them back to Earth. Right? And so what was done then with those rocks was many different kinds of analyses. One of them was to kind of measure the ages of the rocks, compare them with the crater distributions at those locations, and try to use that to recreate the bombardment history of the moon. And when that was done, there were kind of different possible answers. And oh, sorry, I forgot to show the pretty picture of the astronauts walking on the moon. So this is the actual going and grabbing stuff from those landing sites. This is a picture from Apollo 17 landing site. Anyhow, using those rocks, we could actually recreate the impact flux on the moon. And well, what's the answer? Well, the answer is like it depends, right? So one model that was favored a lot early on was that people noticed that there was kind of a clustering in the ages of the rocks. There were a lot of rocks that were aged something like 3.9 billion years ago. And so one interpretation was that the bombardment history on the moon had had this rapid decline after the moon formed, and then it was low, and then there was this cataclysmic spike. And that model was called the terminal lunar cataclysm, or colloquially, the late heavy bombardment. There was other interpretations as well that the bombardment flux had actually just declined smoothly, or that there was a kind of a smaller bump or something else. But the terminal lunar cataclysm was the prevailing model for quite a while. And so in terms of the dynamical instability that we just talked about, well, you can imagine maybe the dynamical instability just happened right there, and it explains that spike. And that's when there was this big shakeup in the solar system that caused a bunch of stuff to bash into the moon. And that was the original proposal by the Nice model, that that was what happened. And you can see in their simulations of things bashing into the Earth and moon, they would indeed find a big spike when the instability happened. And sometimes the instability happened very late. New and now, or not new, but reanalysis of the moon rocks and putting it in a bigger context has kind of changed the story and made us think that that's not the terminal lunar cataclysm is unlikely to have happened. There's been a bunch of different kind of uh, different studies addressing this point, and they all tend to agree now, and they agree that the terminal lunar cataclysm is probably due to sampling bias. And so it's probably that the Imbrium Basin was actually created at about 3.9 billion years ago, but that it launched rocks all over the place. And many of the rocks from different locations were actually associated with one single impact event. And so it's probably not that there was a gigantic bombardment that was late. It's probably the tail end of this smooth decline. That's the current thinking anyway. And so when would the instability have happened anyway? Well, bunch of new analysis has suggested it had to happen early, right? No later than about 100 million years. And this comes from different kind of circumstantial evidence, like the properties of Jupiter Trojans, highly siderophile elements, reset ages in meteorite parent bodies. And there's even some new studies based on different isotopes and asteroid reset ages that suggest that it may have happened very fast, like say at 10 million years after the start of planet formation. So, so earlier, early seems to be when the instability would have happened. And now let me talk a little bit about triggers. So the trigger for the actual instability has got to be linked with the timing, of course. And as of now, there's kind of four possible triggers. And so I'll go through each of them. Here I've kind of listed them in terms of the order when they would have happened. So there's one that's driven by the gas disk itself. There's a second one triggered just by dynamics of the planets. Third one would have been triggered by a star, or actually more likely a brown dwarf or free-floating planet zooming by. And the fourth one is the classical one of the planets interacting with the disk, the planetesimal disk, sorry, not the gas disk, the planetesimal disk. So let me just kind of go through these real quick. So the first one is this basically proposes that the evaporation of the disk itself is the trigger. And so the key part that matters here is in this cartoon on the left, the disk itself in terms of one mode anyway of dispersal of disks is that we think they kind of carve an inner hole and that hole gets bigger and bigger until the disk goes away. And so what would matter then for the purposes of the instability is that the inner edge of that outer region of the gas disk is moving outward. And what that does is it looks like something like this. This is an animation by Bebe Liu. This is a slightly different context. It's for an inner cavity, but it's directly analogous. And so you can see as a planet migrates inward, the cavity moves outward and it pushes the planet with it. And so you can imagine if this kind of behavior was happening out near Jupiter and Saturn and the ice giants, it could move things around. And here's an animation of that happening, where the dashed line here shows that edge moving outward. And as that edge sweeps past Jupiter's orbit, not much happens because Jupiter already carved a gap. As it swept past Saturn's orbit, it did push Saturn outward a bit and kind of squished Saturn into the other ice giants. And that triggers an instability. And so what we found in these simulations is that if the disk goes away like this, it triggers instability pretty much generically. It's really hard to avoid. And so if this is the mode of dispersal of disks, which is debated in the disk community, then but if it is, it would naturally explain a very early giant planet instability. Okay, instability trigger number two is a very simple one, which is that if you plop planets down, they sometimes go unstable on their own, right? So basically, it would be an instability triggered just because planets go unstable on their own, and often fast. So here's a really cool simulation by Grivo et al. From last year. And so the left part here, with all the pretty colors, shows a hydrodynamical simulation of the growth and the migration of Jupiter, Saturn, and three ice giants. Then you can see the gas disk went away, and then within no time at all, right? So this is basically among the best, actually probably the best and most comprehensive hydrodynamical simulations of the giant planets growing and migrating. And then as soon as the gas disk went away, right? And it went away in such a way that it was not that edge sweeping out, just the disk going away everywhere. And then the planets went unstable, right? Immediately almost. And then you could see the instability lasted for 1 million years, and one of the ice giants was ejected, kind of like we saw before. And so planets also just like to go unstable on their own, and they tend to do it fast. It's really rare for a system to wait a long time. Not impossible, but usually if it's going to go unstable, it'll do it fast. All right, instability trigger number three is a flyby, typically of a brown dwarf or a free-floating planet. And so this comes down to the idea that the sun formed within a cluster that probably had a few thousand stars and lasted maybe 20 million years, something like that. Um, And so cartoon version of this, right, going back to this thing, what did the solar system look like kind of during this phase? Probably had the gas giants in this kind of configuration. There was resonant and outer disk of planetesimals. Rocky planets were still doing their thing. The gas disk was going away. And then, a brown dwarf flew by and kicked the planets enough to trigger the instability. That's kind of the simple cartoon version of it. And and so can this really work? And the answer is yeah, it actually works surprisingly well for a certain region of parameter space. So here's some illustration, right? So here's I'll give you a couple different examples. So what you're seeing down here, those straight lines are the orbits of Jupiter, Saturn, and three ice giants. And that big black one is the flyby of a star or a brown dwarf or a free-floating planet. The mass is up here. So it's 27 Jupiter masses in this case. And so in these simulations, we had the giant planets, and also some other stuff. In case you want to know the details, there was a planetesimal disk and the cold classical Kuiper belt out there to make sure that the instability or that the flyby was not so violent as to destroy the cold classicals, which we see today. So in this case, right, a 27 Jupiter mass brown dwarf flew within the orbit of Neptune there, but did not trigger an instability. So sometimes there's a very close flyby and nothing happens, right? Sometimes something happens, right? This is a flyby that was too violent, right? So this thing is 470 Jupiter masses. So what? So it's a what is that? It's a M dwarf star flying within the orbits of the giant of the planets, kind of early in solar system history, but it would have triggered a massive instability that destroys everything. So this did not happen because we have a solar system, right? But this is a possible outcome. Here's another case. This is a very low mass thing, only 8 Jupiter masses, a free-floating planet that flew within the orbit of Jupiter, triggered an instability, and ejected an ice giant. But it actually looks a lot like the solar system today. This is actually consistent quantitatively. It matches the solar system as well as the models that you're familiar with by Nisvorny and so on, right? And so here's a couple more examples that also work. Here's one where the flyby of a 5 Jupiter mass free-floating planet kicked the ice giants and triggered the instability, right? And it matches what we see today. Here's another one that matches just to show you another illustration. And here's an interesting one where the system got kicked early on, but didn't go unstable for like 50 million years. And so then it was a flyby triggered instability, but it's hard to tell because it happened so late, right? So this is a tricky case, but it happens. And here's kind of just a simple cartoon of putting this in a simulator of encounters within a cluster. What you see here is basically the closest approach of different stars that are always flying by the sun. So they typically, the typical flybys that happen all the time happen at several thousand AU, and they don't really affect the planet's orbits directly. But once in a while, there's a closer one. So in this case, if you look, on the x-axis is time. Once the color of those dots turn blue, that's kind of when a, a flyby triggered the instability. And so you can see the small dot here, the first blue dot with a flyby at 30 AU or so triggered an instability. And the solar system all of a sudden underwent instability and looks more or less like it does today. But then a few million years later, there was another close flyby that kicked the system too much. And in this case, I think it destroyed the cold classicals, basically made it so the solar system does not look like it does today anymore. And so you can see there's constraints you can put on the evolution of the sun and the birth cluster from what the solar system looks like today. And so in practice, starting, with the sun being a birth cluster, we try to do things of trying to see what conditions are needed to match, in a successful way, the actual solar system. And there's also the other ones, conditions that are needed to avoid things that didn't happen. And put together, you can constrain basically the parameters of the sun's birth cluster. Anyhow, moving on, the fourth and last instability trigger is basically interactions between the planets and the planetesimal disks early on. It's the same as the cartoon I showed you earlier. This is the classical trigger for the dynamical instability, the one that was investigated from the start, and most people think is just the trigger. And the truth is, it's the worst of the triggers. It's the least likely to be the one, I think. But it still works, and it still can create an instability. And so in terms of timing, right, I listed the rough order of timing, but let me put numbers on it. So the disk-driven instability would happen very early, within like 5 million years after the start of planet formation. The self-triggered one would have happened within a few million years of the gas disk going away. The flyby one would have happened during the cluster phase, most likely, which is within, say, 20-ish million years. And then the planetesimal disk-driven one, according to current studies, wouldn't have happened for maybe 30 to 60 million years later. And based on the cosmochemical constraints, right, there's no firm timing where we know it happened exactly then, but they're all leaning earlier and earlier. And so I think the most consistent ones are these three. And the planetesimal disk one is not impossible, but it's definitely not favored right now, in my opinion. All right, now let me switch gears and talk about how this connects with Planet Nine. So you have all probably heard of Planet Nine, right? And its existence has been invoked to explain the orbital distribution of basically sednoids or extreme trans-Neptunian objects, if you like to call them that. And so it can explain why their perihelia all lie on one side of the sun, basically. And this is a big debate as to whether they really do or not, or whether this is an observational bias. But let's go with the idea, right? So the observed distribution, this alignment of extreme TNOs or KBOs, whatever you want to call them, it, can be maintained by a Planet Nine with a mass of, say, 5 to 10 Earth masses. The solar system's obliquity can also be maintained by that. And there's actually another population of low inclination Neptune crossing objects that actually have a stronger signal in terms of evidence for Planet Nine as well. So Planet Nine may really exist, right? It's uncertain if it really does, but it could. And so it would be on this, say a 5-ish Earth mass object on an orbit that's maybe 300-400 AU in semi-major axis that's pretty eccentric, right? With an eccentricity of like 0.5 or something like that. And so in terms of the kind of mass versus orbital separation, what you can see here is the exoplanets are these dots, right? The colored dots. The solar systems are the pictures, and Planet Nine would be this light blue point out here. And what you can see is basically there's a bunch of other exoplanets that have been detected by direct imaging that do have very wide orbits. And there's a couple that are pretty well nailed down that really are wide orbit planets. And so whether or not Planet Nine actually exists, there do exist wide orbit planets. And that's interesting. And so let's see how they can fit into a bigger picture. So the origin of these wide orbit planets is weird. Just like this picture is kind of weird. Yeah. And so why is it weird? The simple reason is just that the orbits of these planets are much bigger than the sizes of planet-forming disks. So planet-forming disks are typically 30 to 100 AU, according to the surveys done by things like ALMA. Whereas the orbits of these planets are 10 times larger, right? And that's weird, right? The sun's disk, we have some good indirect information, right, due to the deficit of high inclination TNOs, that the sun's disk was probably something like 80 AU in size, right? So even the sun's disk was not a giant disk, because there do exist a few disks that are 1,000 AU in size. And so maybe Planet Nine could just have formed one of those, but that's not the case because we think the sun's disk could not have been bigger than about 80 AU. Another kind of indirect piece of evidence is that the exoplanet occurrence rate seems to peak, this is only data for really giant exoplanets, but the data seems to peak between 1 and 10 AU in terms of their occurrence, not increasing out to larger distances. So that's kind of circumstantial evidence that most planet formation happens closer in, not out at several hundred AU. So, where did Planet Nine come from? Probably not just forming in situ within a giant disk. So the only other scenario, apart from the one I'm going to talk about in a sec, that you could imagine that might work is that Planet Nine could have just been captured from another star, maybe during an encounter during the birth cluster phase. So here's an animation of this. We went into this after Planet Nine was first proposed, and it can happen, right? So here's the sun is that big blob on the left, and another star is going to come by, and that black thing is Planet Nine, right? So that's a planet around this other star that's already on a very wide orbit, and it can get captured by the sun. And those red dots are just planetesimals getting kicked all over the place because we were testing whether they follow the right alignment. And they can sometimes. So this kind of thing is possible. Planet 9 could have been captured from another star. To get the right orbit and the right circumstances is tricky. And when you put all the numbers in there, the odds are very low. For typical numbers, the odds are more like 10 to the minus 3, 10 to the minus 4. If you crank everything up the most you could reasonably, the odds are about 1%. Right? So it's not impossible, but not terribly likely either. But let's go back to, right, stars forming clusters. Clusters last to maybe 10 or 20 or 30 million years. So there's some time in there when planets are forming and stars are nearby. So what happens there? And so let's look at this more closely. So what this animation shows here is let's imagine that the solar system's dynamical instability happened during the cluster phase. Here, we're not talking about a star triggering the instability. We're just going to kind of assume the instability was triggered by itself. We're going to assume it's kind of more or less self-triggered. But we'll keep track of stars flying by and see how they affect objects on their way to being ejected. Right? And so what you see on the left is the cluster itself that has only a few hundred stars in this case. The sun is anchored to the origin, so you see all the other clusters wobble around. And then on the top right is an XY plot of the sun, and on the bottom right is a parameter space plot. And so you can see from the bottom right plot that the instability was just triggered and that ice giant is getting kicked out and on its way to being ejected. It's getting kicked to higher and higher eccentricity. And then you can see what happens, it's being kicked, right? And then other stars fly by. So that star just flew by and it changed its orbit. So it kicked it to a lower eccentricity. And so here, another one's going to happen right in a sec. Oh, no. And yeah, so there you go. That was a pretty strong one, where the star flew on the other side of the sun, and basically the indirect impulse dropped the eccentricity of the planet way down. It was getting scattered. Its eccentricity was above 0.9, and all of a sudden it got dropped down to 0.3 or so. But this process keeps happening while the cluster is around. And in this case, we dissipated the clusters after 3 million years. Right? And then the clusters go away and there's still some flybys, but not a lot. And then at the end of this simulation, you can see that planet stranded on a 5 or 600 AU orbit with an eccentricity of like 0.4 or 0.5. It's a good analog for Planet 9, right? And so in this scenario, Planet 9 would have been that third ice giant that was kicked outward and ejected, but it wasn't actually ejected all the way to interstellar space because of the flyby of a star. It was captured on a wide orbit. And so we repeated this kind of simulation for many different cases. And so we repeated it for both of the solar system instabilities, both the formation of the ice giants and the giant planet instability. And what these plots are showing is basically the final orbits of the planets in different setups that you can see in each panel. And so there's tons of information here. But the key thing to take home here is that on the left in the plots are basically the surviving planets, and on the right are the planets that get kicked out and kind of saved in this Planet 9 kind of way. And exactly where they are depends on what happened, right? It depends on things like the density of the cluster, how many stars are flying by, and also the properties of the planets doing the kicking. And so, like I said, these are the top two rows are for the solar system, and the bottom row is for exoplanet type systems, right? Either ice giants or gas giants, or even a case of circumbinary planets. That's the bottom right-hand one. Right? And so there's too much to talk about, so I'll move on from that one. But let me kind of illustrate the general cartoon of what happened, right? So a planet being scattered outward by Jupiter and Saturn, like we saw in the animation, right? What happens is the planets get kicked out. It also always comes back and crosses the orbits of the planet. So it gets kicked out, and then it gets another kick and gets kicked to a higher eccentricity, but it keeps coming back to that point. Get kicked to a higher eccentricity, but it keeps coming back to that point. And so ejection will happen when it finally gets a kick that gets, this random walk in energy that gets enough energy never to come back. But in the meantime, if a star flies by and gives a kick from the other side, it can change the pericenter, and all of a sudden the planet is saved onto this stable orbit. So that's the mechanism that can basically strand planets on Planet 9-like orbits. And the efficiency with which that happens depends on these circumstances. And so here's basically the trapping efficiency is the y-axis. And what does that mean? That means the probability that any given planet that's ejected will be trapped on a wide, stable orbit. And so what you can see is for circumbinary gas giants, the odds are basically 0. And the reason for that we'll come back to in a second. It's basically the kicks are too strong, right? Ice giants and extrasolar gas giants are also pretty unlikely, but the solar system cases are pretty good, right? The success rate, the trapping efficiency is about 5 to 10% typically. And you can see even among the exoplanets, the solar system-like case with Jupiter, Saturn, and one ice giant is by far the most, highest trapping efficiency case, which is interesting. And so if you put these numbers together, if you assume about 5 planets were ejected from the solar system, right? 4 in that first instability that formed the ice giants, and then 1 in the dynamical instability, and you do binomial statistics on this, the probability of capturing a wide orbit planet like Planet 9 is about 40%. Right? That's 40 times more than the cranking up numbers of the capture model, right? So this is if Planet 9 exists, this is how it would have got there. And so just to illustrate, why don't, exoplanets like gas giants do a better job, giant exoplanets do a better job of trapping planets. It's really simple. Basically, if they're a system with a bunch of Jupiter mass planets, or say a circumbinary system, as it's scattering another planet, it ejects it too fast. So the time frame during which there's a wide orbit that's vulnerable to passing stars is very short, right? And the opposite is true for systems of ice giants, right? They like to kick things out, but it takes forever because their kicks are much weaker. And so by the time, the planet in ejection reaches a very wide orbit that's susceptible to getting kicked from the outside, the cluster's already gone. Of course, sometimes planets are indeed ejected, and we find them now. There's hundreds that are known, found with tools like JWST and plenty of other telescopes too. And for example, this image comes from a study of Upper Scorpius, where we found about 100 free-floating planets, just within that one star forming region. And the goal now is to understand what fraction of these, free-floating planets are really planets that were ejected versus something closer to failed stars. And that's kind of where the field of free-floating planets, at least by direct imaging, is at right now, is trying to be able to put strong constraints on what fraction come from each mechanism. I think it's inevitable that some get ejected, but are those the ones that we're seeing here or not? That's up for debate. So let me wrap up. So kind of the key things I talked about were kind of the 2 solar system instabilities, right? The formation of the ice giants, and then what's traditionally called the dynamical instability. There's a probability of about 40% that, a wide orbit planet like Planet 9 could have been captured during those instabilities in the solar system, given the sun being within within its cluster. And putting the numbers on there, basically, and extrapolating to exoplanets, this kind of study predicts that at least, 1 in 1,000 stars should really have a Planet 9 around it, and maybe more, up to about 1 in 100. And some of those are being found now, which is pretty cool. And finally, the tool with which we're going to have the answer as to whether Planet 9 exists is LSST, the Vera Rubin telescope. And within not long, like a year or two, we'll have the answer. Whether or not Planet 9 is found, if they actually find a blip that's moving and say, there's Planet 9, right, then we'll know. But they may just have much, much better statistics on the properties of distant trans-Neptunian objects. So you can tell very clearly whether the existence of another planet, planet 9 is consistent with that or not. Indirect evidence or evidence against, I think it's much more likely than really finding it right away. And if you want more information on this, here's kind of the key references of the stuff I talked about. That second one, the paper about the instability being triggered by a flyby, I did submit a couple weeks ago. And I also read a blog in which I sometimes talk about solar system formation. It's called Planet Planet. All right, I'll stop there. So thank you for any questions.
Thank you, Sean, for a very great and very interesting talk. There was some discussion at the chat about that the distribution of observed giant exoplanets is observational bias and can tell us nothing related to where planets are. So did you also take that into account?
Oh, sorry. So what the distribution of giant is observational? I mean, so all right. So I see this comment. The distribution of observed giant exoplanets is biased and can tell us nothing related to where planets are. Oh, okay. I think that's related to the radial extent. And so let me go back to that plot because I think it's really interesting. So that's the one about I think it's this plot that we're talking about, right? All right. So if this is the
Yeah.
plot we're talking about, then you know, the fact that the curve rises as you go further out means that you can find basically, it's harder and harder to find planets to the right, at least by the techniques. These are all done with radial velocity, right? All these studies. And the question is whether you can really be confident in the downturn beyond a given distance. And that's really hard to evaluate, right? That depends on statistics and so on. So I'm not sure, right? It seems like several different groups are converging on the same answer, which is encouraging. But, whether you can really be confident in that downturn past 3 AU, I don't know, right? That's a very tricky question to ask. And so taken at face value, it tells you something. The truth is it can't keep going up and up and up forever out there because then direct imaging would have found a lot more planets further out, right? The direct imaging constraints are pretty strong these days. And so there definitely are not a lot of planets out at 50 AU, right? Between 5 and 50 AU, I think the numbers are fishy, but beyond 50 AU, there's not a zillion planets out there. And so whether or not the downturn is in the exact right place, I don't know. I don't know, but it's a good question. I'm not sure. Oh, I see
Uh,
there's a direct question on that, so we can
yeah,
maybe
yes.
another comment on.
Sorry, that was for me. Yeah, okay. So basically, when it comes to this thing, it is very tricky to say in the sense that direct imaging is mostly like to show you exoplanets that are young and they are emitting so that they're bright. So then from directing imaging, you're not going to get a heck of a lot when it comes to statistics otherwise. You probably won't be able to see them unless we get some very, very, very sensitive instruments out there, like possibly the ELT. And then on the other hand, radial velocities, again, are going to be very difficult because you need to have something particularly massive to be seen. So again, any smaller gas giants, you're not going to see them. So
Yeah.
I wouldn't. Of course, it's not going to increasing all the way whenever, but again, there are disks that are very massive, and they are producing even 2 Jupiter masses planets or more. So again, you're only going to be able to see these if they're very young.
Sure, sure. I know there's cases like HR 8799 where there are indeed super Jupiters out at the outer ones at 75 AU, something like that. But at the same time, given the statistics on disk sizes these days that are getting pretty good, right? The fraction of stars that have disks larger than 100 AU is pretty small. And so
Yes,
my
true.
take is that the idea of there being a humongous population of planets out there that would have formed locally is pretty unlikely.
I'm not saying it's going to be a humongous. I'm saying just be very careful with this 1 AU because it's likely not going to be true. Also, yes, there is a lot of disks being characterized in molecular clouds, But you have to be very careful, because to characterize very well these disks, you need to look for molecular clouds that are very close to our system, which means low mass stars. So even if you were to go to slightly bigger, like A stars, because okay, then it becomes a problem that you're not forming planets in bigger stars, likely, but you're going to have
Oh, I lost what was being said there at the end. Oh. I think she cut out.
Yeah. It seems like she's trying something.
Okay. Are there other questions I should ask?
She also asked in the chat, like, you showed the 4 models, and what are the like initial conditions of these models, and do they fit with the results of planet formation models?
Yeah, so which models was she referring to there? Do you know? I mean,
The 4 models that you showed us, that
for the instability time, the
yes.
trigger thing. Yeah, they all start from the same thing, from basically from planet formation models. Yeah, so they're all consistent with at least the best thing we have now for the planets forming within gas disks, and then the gas disks going away in one way or another.
Okay, thank you. Does anybody else wants to ask questions? I also have a question. You said like, okay, I'm asking question about the planet 9. Like the planet 9, you basically said is from it is captured from another star, or it's formed in the solar system but then got into another orbit. But is it also possible that it could have been captured, the sun captured the planet 9 from a free floating planet that just got too close?
Oh, that's very hard to do. It's I don't, let's see, how would you capture it on an orbit like that? I I think that's a very tricky one. So to have it captured on an orbit like that from a free-floating planet, the free-floating planet would have to kind of cross over, come within Planet Nine's current orbit, and then it would have to get a big gravitational impulse to capture it. And there's nothing there to do that. Because all the planets, the key thing about Planet Nine is that it's not crossing the orbits of the other planets. It's significantly separated from them. And so it would be very tricky to do that, to
Okay.
capture it without it crossing the orbits of the planets, unless it was right as another planet was being ejected and it happened to run into it, which is obviously not impossible, but the odds would be very low.
Okay, thank you. Dimitri has a hand raised, so you can ask the question.
Yeah, hello, Sean. Nice to see you. Very nice talk. Thank you. I was a little bit late. Good to see you. I have a bit philosophical question. Like in the solar system, we have this empirical Titius Border law that essentially explains relatively well the positions, at least of the planets, meaning that there is like high degree order in the end, right? Which also means why we are here, because the conditions were relatively stable. But of course, we also know that there were these periods of chaos, of instabilities. And so, but at least in our case in the solar system, let's say the high degree order has prevailed in the end. And I'm just curious, what would be the kind of the guiding force, the process that allowed it to happen? Is it indeed what you were saying? Let's say if it was the formation in a clustered environment that disappeared, and the degree of chaos dropped eventually, or it's just the planetesimal interactions themselves that go to kind of orderly state in the end if you wait long enough?
All right, so that's an interesting question. So yeah, so the key thing from like the Titius-Bode law that I think is the takeaway is that planets are spaced kind of geometrically or logarithmically or whatnot, not linearly around a star. And then the numbers are put into work, and there's various things about that. But so where did that come from? Well, what that comes from, I think, is that what is the criterion for stability within a planetary system, right? When you go into the numbers, what is it that makes, the orbits of 2 or 3 or 4 planets stable versus not? And there's been a bunch of studies on this, and you can see it very clearly if you do simulations of this stuff, is that the kind of the key parameters are either resonances, where they can trap things and make them stable, like a long chain of resonances, or if it's the case, the resonance is not stable, then it's determined by this thing called the Hill radius, right? Kind of measure of the Roche lobe in the sun's potential. And both of those have a dependence on the distance of the star. They both predict basically geometric or logarithmic scaling of planetary orbits from the sun. And so you can think in some sense, if you throw anything around a star, it's going to crash together, it's going to go unstable, it'll do whatever it does, and whatever survives is generically going to follow something that looks like a Titius-Bode law because it has to end up with this, the stable islands within the sea of possibilities have that kind of spacing. And so I think it's just a survival mechanism that anything that's not there doesn't last very long because just based on the physics of the orbital dynamics, the stable things like to space themselves that way.
Oh, thank you. Yeah, that makes sense. Yes, thanks.
Yeah, we also have a question from Diego.
Diego, how's it going?
Pretty well, thank you, Son. About the philosophical points you were making in the presentation, there are a couple of things that I think should be framed slightly different. One is the fact that, yes, it is true that the instability model is the only scenario that fits the structure of the solar system, starting from a very well-determined set of initial conditions, as you also pointed out later in the talk. We don't know what are the initial conditions of the solar system. You're doing the reversing problem in something that is very degenerate. So you might find an island of solutions, which doesn't mean that it is necessarily the correct one. Like for Jupiter, we have models saying that Jupiter formed at 5 AU, at 10 and migrated, or even at 40 AU and migrated. So, and all of them fit some cosmochemical constraint and some of the other. And basically, for all the cosmochemical and architectural constraints that we have on the solar system, they can be explained by formation alone in one way or another without invoking the instability. So it is tempting, the fact that there is a well fit, but it doesn't mean the initial condition are necessarily the correct one. For example, the Rickman paper that you were mentioning also about the effect of the birth cluster on the instability starting from the 5 planet condition. That paper finds that in terms of dynamical excitation, you can get the solar system both without having an instability, so a light push that produces the excitation, but you don't undergo an instability, or it could be a very delicate instability, but there is like an uncertainty region there. You can obtain the same final results from 2 different evolutionary paths. So we still don't have any proof at the moment that the solar system underwent an instability. We have, as you said in the abstract, circumstantial evidence that, however, is not unequivocal.
Sure. I mean, that's a good point, right? The instability does a great job of getting from point A to point B. And, you have to trust something in, about point A. Is point A realistic or not?
Yeah,
And
but for example, in the Kevin Walsh initially Grant-Tuck scenario, it explained the low mass of Mars, but the initial conditions were completely wrong. It was starting with a dynamical cold disk with Jupiter already formed. And also you in 2017 showed, and we, as well as other people, I did it in 2014. This basically is not true. The moment you form Jupiter, you don't have a dynamically cold disk. It's already reshuffled. So again, yes, you need to trust A, but we need to pay a lot of attention if A is reasonable or not, and not just put blind faith, because the result is what we want.
Yeah, sure. I mean, if you have a thing that gets you from A to B, then the question is how do you get to A, and then you got to rewind and go to that, or find some other path to get to B. Sure.
And if there is a bit of extra time, and I can take advantage, I wanted to ask you a question about instability related, if there is no other person that wants to ask.
Yeah, I think you can go ahead.
Okay, so I saw that across the summer there was a paper in which you were co-author by Sarah Joret, I don't know how it's pronounced.
Yeah.
And basically it was claiming that asteroids cannot retain water by impacts because otherwise during instability you would have created the water signature in the diogenize. You don't see the signature, so the asteroid should have failed retaining water.
Okay.
There is a missing part in this picture that I am curious to see if it was analyzed, because the paper quotes one of my work in which I make this point clearly, that is, when you do impacts during instabilities or formation, you have accretion, but you also have erosion, always balancing the two. And the paper doesn't discuss erosion, but the kind of instability, the kind of bombardment flux that it produces and described in the paper is so violent that would have destroyed Vesta. So actually the paper seems to say, no, we didn't have an instability, otherwise we wouldn't have had Vesta. There are impacts at 40 kilometers per second there.
I see what you mean. So it was too violent, and so even though you couldn't retain water in the calculations she was doing, there's more to the story, and it would actually be smashing Vesta to pieces.
Yes.
That's a good point. I mean, you're right. That would be another constraint. Like you can't have anything past a certain threshold in energy or whatever to erode it. Sure. No, that's a good point. That's a good point. I don't think she took that into account. No. Yeah, you're right. To have a coherent picture, you need to have both sides of that. So yeah, that's a good point. I mean, it's like analogous to the flyby triggered instability thing I was talking about. We included, a ring of planetesimals out where the cold classicals are, and that was kind of, there's a constraint that they cannot have been excited past a certain level, the one we've seen today. Otherwise, the flyby is not consistent, right? Even if the flyby of a whatever, a brown dwarf triggered the instability and makes everything else look good, if it messes up the cold classicals, then it's not what happened. And so you're right. And so clearly defining those kind of things of exactly what are, conditions for success or not in a model is pretty important. And so sometimes we miss them. So.
Yes, in this time I will need to drop a line because it was described in the paper that is cited there, and it actually negates the very title of the paper. So I will talk with Sarah.
Yeah, sure. Let her know. Sure. Yeah, I mean, yeah, we can talk about numbers and stuff. I don't have off the top of my head exactly the details, but I'm sure she'll know. So. Cool. All right. Any more questions or?
I think we should end it here. And if you have any more questions, I think they can write to you.
Okay.
Thank you again very much for coming to give a talk at our seminar.
Yeah, it was a pleasure.
Yeah. Cool. Thanks again. And I think that will be the end. So have a nice week ahead.
Thanks. You too. Take care, everyone.
Bye.
Bye.
Bye-bye. Bye.
Goodbye.